Welcome back into the dark. On the 27th of December, 2004, a signal crossed 50,000 light-years and reached Earth. It lasted 0.2 of a second. In that breath, a dead star no wider than a city released 250,000 years of sunlight. Every gamma-ray satellite in orbit saturated at once. The sky above your head changed, ionized by something that happened on the far side of the galaxy. Tonight, I want to take you to that night and show you how the universe builds something so extreme it can only exist for 10,000 years before falling silent forever. If this journey resonates with you, leave a small light behind, a like, a subscription, so others may find their way here too. Lower the lights now. Put on your headphones. Let the weight of the day fall away. We are about to travel 50,000 light-years across the galaxy to visit the brightest explosion ever recorded outside our solar system. A signal that arrived on the day after Christmas in 2004, carrying with it 250,000 years of sunlight compressed into 1/5 of a second. You do not need to hold on to anything. Just let yourself drift and we will take you there. I am the cartographer of the dark, and I have been mapping these distant places for longer than I can remember. Tonight we follow a signal that crossed 50,000 light-years, carrying a story written in the collapse of a crust harder than diamond. On the morning of the 27th of December, 2004, something happened on the far side of the galaxy. A signal began its journey across 50,000 light-years of empty space, moving at the speed of light, carrying with it the signature of an event so extreme that when it finally reached Earth, it would rewrite what astronomers believed possible. The signal arrived 0.2 of a second before anyone understood what they were seeing. Every gamma-ray instrument in orbit saturated at once. Not sequentially, not one after another as the Earth turned, but simultaneously, as if someone had thrown a switch across the entire planet. Satellites designed to measure the faintest whispers from dying stars were blinded in an instant. The detectors maxed out, unable to record the full intensity of what was pouring through them. It was the brightest gamma-ray flare ever recorded outside our solar system, and it came from a single object no wider than the city you might live in. The object had a name: SGR 1806-20. A magnetar, hidden behind the center of our galaxy, in the constellation Sagittarius. A region so thick with dust and starlight that optical telescopes cannot see through it. 50,000 light-years away, on the opposite side of the Milky Way, a star the size of Manhattan had cracked its own crust. In those first 200 milliseconds, SGR 1806-20 released as much energy as our Sun radiates in 250,000 years. Not 250,000 days, not 250,000 hours, 250,000 years of sunlight, compressed into 1/5 of a second, and flung across half the width of the galaxy. The flare was so bright that its reflection off the surface of the Moon was detectable. Astronomers would later use that reflected light to reconstruct what their instruments had been too overwhelmed to measure directly. The signal did not merely reach our satellites. It reached into the atmosphere itself. The ionosphere, the layer of charged particles that wraps around our planet and reflects radio waves, changed. Its density shifted. For a brief moment, the night side of Earth responded as if the sun had risen. Victoria Caspi, an astrophysicist at McGill University, would later describe it plainly. The flare changed our ionosphere from night to day. All of this from an object 50,000 light-years away. If you could see gamma rays the way you see visible light, the flare would have appeared brighter than the full moon, but only for a fraction of a heartbeat. Then it faded into a long, oscillating tail, a dying pulse that continued for minutes, the star ringing like a bell that had been struck too hard. This was not the first time a magnetar had done this. Twice before, astronomers had recorded giant flares from distant neutron stars, once in 1979 from an object designated SGR 52666, and again in 1998 from SGR 1900+14. Both events had been extraordinary. Both had pushed the limits of what detectors could measure, but the 2004 event was 100 times more energetic than either. It was not an incremental step. It was a leap into a new category of cosmic violence, one that required a different kind of explanation. The explanation begins with distance. 50,000 light-years is not a number that fits comfortably into human intuition. It is half the diameter of the galaxy. It is the distance light travels in 50,000 years, moving at 300,000 kilometers every second, never slowing, never stopping. If you could board a spacecraft tomorrow and travel at the speed of light, you would not reach SGR 1806-20 until the year 52,024. Your journey would span the entire written history of human civilization twice over. And yet the light from the 2004 flare, which left the magnetar 50,000 years ago, arrived here on a December morning, while people were opening gifts and making breakfast and going about their lives, unaware that the sky had just been rewritten. The signal that reached us was an echo. The event itself, the moment the star cracked and the field released, happened 50,000 years in the past, when humans were still painting on cave walls and the last ice age had not yet ended. The light has been traveling ever since, crossing the spiral arms of the Milky Way, passing through clouds of gas and dust, threading the space between stars, until it finally intersected the orbit of a small blue planet on the inner edge of one of the galaxy's minor arms. At 50,000 light-years, the flare was a whisper that ionized our atmosphere and saturated every detector we had pointed at the sky. Astronomers would later calculate what would have happened if SGR 1806-20 had been closer. If it had been within 10 light-years of Earth, the distance to our nearest stellar neighbors, the flare would have stripped away the ozone layer. It would have triggered mass extinction, the gamma rays would have reached the surface, and the chemistry of life would have unraveled in minutes. But it was not 10 light-years away, it was 50,000. And so we are here, and the flare is a dataset, a collection of measurements, a story we can tell because we survived to tell it. SGR 1806-20 is a magnetar. That word will carry weight as we move deeper, but for now it is enough to know this. It is a neutron star, the collapsed core of a star that died in a supernova, and it possesses the strongest magnetic field ever measured in the universe. The field is so intense that it warps the behavior of matter and light in ways that no laboratory on Earth can replicate. It is a star that should be dead, silent, cold. Instead, it is one of the most active objects in the galaxy, capable of releasing more energy in a fraction of a second than our Sun will produce in 250,000 years. The 2004 event was not an explosion. It was not a detonation in the way we usually imagine. It was a starquake. A fracture in the crust of a star so dense that a sugar cube of its material would weigh as much as all of humanity. The crust cracked. The magnetic field, which had been building stress for years, suddenly rearranged itself. And the energy that had been stored in that field, locked in the geometry of twisted magnetic lines, released all at once. Lower the lights. Put on your headphones. We are going to follow that signal backward, across 50,000 light-years and 50,000 years, to the surface of a star that should not exist, and watch what happens when the universe builds something so extreme that it can only survive for 10,000 years before burning itself out. If you are ready to drift, this is the place to begin. The story of the magnetar is the story of the briefest, most extreme life the cosmos has ever written. And it begins not with a birth, but with a crack. I wonder which part of the world is listening right now, in the dark. The stars look different from every place on Earth. If you'd like to leave your city and local time below, I'd be genuinely curious to know. A neutron star is what remains when a massive star dies. The outer layers explode outward in a supernova, and what survives is the core, compressed by gravity into something that should not exist according to the intuition we carry from living on a planet where things fall gently and water finds its level. The core that remains contains roughly 1.5 times the mass of the Sun, but it no longer occupies the space a star requires. It has been crushed into a sphere about 20 kilometers across, roughly the size of a city. You could walk from one edge to the other in an afternoon, if the surface did not spin hundreds of times per second, and if the gravity did not flatten you into a layer thinner than a single atom. The density of a neutron star is not something we encounter elsewhere. Take a sugar cube, the kind you might drop into tea. If that cube were made of neutron star material, it would weigh as much as every human being alive, combined. The mass of 8 billion people, compressed into a volume you could hold between your thumb and forefinger. A teaspoon of neutron star matter would weigh approximately 1 billion tons on Earth. There is no analogy that makes this comfortable. The numbers resist the imagination. But the object is real, and there are millions of them scattered across the galaxy, silent and spinning. The densest ordinary matter the universe permits before gravity collapses everything into a black hole. Inside a neutron star, atoms no longer exist. The pressure is so extreme that electrons are forced into protons, creating neutrons, and those neutrons are packed so tightly that they touch. The star becomes a single atomic nucleus, 20 kilometers wide. The surface is smooth, hard beyond any material we know. Mountains on a neutron star, if they exist at all, rise no more than a few millimeters, because gravity does not permit anything taller. The crust is a crystal lattice of iron nuclei, and beneath that, layers of increasingly strange matter descend toward a core we cannot see and do not fully understand. The deeper you go, the less certain the physics becomes. At some point, perhaps a few kilometers down, neutrons may begin to dissolve into their constituent quarks, or arrange themselves in configurations that have no name in our textbooks. We do not know. No experiment on Earth can recreate the pressures that exist in the core of a neutron star. We can only observe from a distance and build models that approach, but never quite reach, the truth. Neutron stars spin. When they form, they inherit the angular momentum of the collapsing core, and because they are so small, they spin extraordinarily fast. Some rotate hundreds of times per second. The conservation of angular momentum is absolute. A star that once took weeks to complete a single rotation collapses into an object the size of a city, and suddenly spins faster than a helicopter blade. The equator of some neutron stars moves at a significant fraction of the speed of light. The spin is not optional. It is written into the physics of the collapse itself, a consequence of the fact that the universe does not allow rotational energy to simply disappear. Many neutron stars emit beams of radio waves from their magnetic poles, and as the star rotates, those beams sweep across space like a lighthouse. If one of those beams happens to point toward Earth, we detect a pulse, regular as a clock, sometimes more precise than the atomic clocks we build to measure time itself. We call these objects pulsars. A pulsar is simply a rotating neutron star whose beam we can see. The name describes our perspective, not the star. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who noticed a signal repeating every 1.3 seconds, so regular that it was briefly considered as a possible transmission from an extraterrestrial civilization. It was not. It was a neutron star, 12 miles wide, rotating once per second, its radio beam sweeping past Earth with the regularity of a metronome. Not all neutron stars are pulsars, and not all pulsars are alike. Some spin once per second. Others spin so fast that their equators move at a significant fraction of the speed of light. Some emit radio waves. Others emit X-rays. A few emit nothing we can detect, and we find them only by the way they bend the light of stars behind them, or by the faint heat they radiate as they cool across millions of years. The galaxy contains perhaps 1 billion neutron stars, most of them invisible, most of them cooling quietly in the space between spiral arms, undetected and unremarkable, except for the fact that they exist at all. And then there are the magnetars. A magnetar is a neutron star, but it is not an ordinary one. The distinction lies in the magnetic field. Where a typical neutron star might have a magnetic field 1 trillion times stronger than Earth's, a magnetar's field reaches a quadrillion times stronger, sometimes more. The difference is not one of degree, it is a difference in kind. The magnetic field of a magnetar is so intense that it dominates the star's behavior, its structure, even the space around it. The field stores more energy than the star's rotation. It warps the crust, twists the interior, and occasionally tears the surface apart in events we can detect from across the galaxy. Magnetars are rare. Astronomers have confirmed only a few dozen, though there may be many more that have gone quiet and no longer announce themselves. They represent a specific outcome, a narrow set of conditions at the moment of collapse. Not every massive star becomes a neutron star, and not every neutron star becomes a magnetar. The path is narrow, and the window is brief. But before we can understand what makes a magnetar different, we need to hold in mind what a neutron star is. It is the remnant of a star that once burned for millions of years, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, climbing the periodic table until its core filled with iron and the fusion stopped. Iron does not release energy when it fuses. It absorbs it. The core could no longer support itself. It collapsed in less than a second, and the rebound sent a shock wave outward that tore the star apart. What remained was this: a sphere the size of a city, containing more mass than the sun, spinning in the dark, cooling slowly, a monument to the violence that created it. A neutron star is not a star. It does not burn. It does not fuse. It simply exists, radiating away the heat of its birth, spinning down over millions of years, until eventually it becomes too cold and too dim to detect. It is a corpse, but it is not inert. It is the densest, strangest, most extreme object in the universe that is not a black hole. And in a small number of cases, under conditions we are only beginning to understand, it is born with a magnetic field so powerful that it changes everything. The taxonomy is simple. A neutron star is the parent category. A pulsar is a rotating neutron star that emits beams we can see. A magnetar is a neutron star with a magnetic field strong enough to crack its own crust. The distinctions matter because the behaviors are different. A pulsar spins down gradually, losing energy as it radiates. A magnetar does not spin down gracefully. It fractures. It flares. It releases in milliseconds the energy it has been storing for years. That is what a magnetar is built upon. That is the foundation. A city-sized sphere of neutrons, spinning hundreds of times per second, with a crust harder than diamond and a core we cannot see. The magnetic field comes next, and with it, the starquakes, the flares, the brief and brilliant fury that reaches across the galaxy and arrives here 50,000 years later, as a flash of gamma rays that changes the sky for a fraction of a second before fading back into silence. We have already met the neutron star, that city-sized remnant of a collapsed sun, its mass pressed into a sphere 20 kilometers wide. We have walked across its surface in our minds and felt the weight of 1 billion tons balanced on the edge of a sugar cube. But a magnetar is not simply a neutron star. It is a neutron star wrapped in a field so intense that it rewrites the rules. A magnetar's magnetic field reaches a quadrillion times the strength of Earth's. The planet beneath your feet carries a field of half a Gauss at its surface, enough to guide migrating birds and turn compass needles toward the poles. A refrigerator magnet, the small rectangle holding a shopping list against cold steel, measures 100 Gauss. The MRI machine in a hospital, its field strong enough to pull metal objects across a room if safety protocols fail, reaches 10,000 Gauss. An ordinary neutron star, already an object of extreme physics, carries a magnetic field of 1,000,000,000,000 Gauss. A magnetar surpasses even that by a factor of 1,000 or more, climbing toward a quadrillion Gauss and beyond. You can climb this ladder one rung at a time. Earth. Refrigerator magnet, MRI machine, neutron star. Magnetar. Each step is a leap of orders of magnitude, and the final step is the longest. The field at the surface of a magnetar is more than 100 million times stronger than the most powerful magnetic field humanity has ever created in a laboratory. And those fields existed only for fractions of a second inside controlled explosions. A magnetar sustains its field for thousands of years. At this intensity, the field does more than attract and repel. It bends the behavior of matter itself. Atoms elongate into thin rods, their electron clouds stretched along the field lines until they no longer resemble the spherical orbitals sketched in textbooks. Chemistry as we know it ceases. The bonds that hold molecules together, the forces that allow proteins to fold and cells to divide, cannot exist in such a field. Biology is impossible. Even the simplest structures of matter are reshaped, but the field reaches further still. It reaches into the vacuum itself, into the space between particles where we once believed there was nothing. Quantum electrodynamics tells us that empty space is not truly empty, that it seethes with virtual particles flickering in and out of existence, that the vacuum has structure. Near a magnetar, that structure becomes visible. The magnetic field is so intense that it polarizes the vacuum, bending light that passes through it even before that light reaches the surface of the star. Physicists call this vacuum birefringence, a term borrowed from the behavior of crystals that split light into two rays. Here, the crystal is space itself, and the field is the force that cracks it open. Light approaching a magnetar does not travel in straight lines. It curves, it splits. Its polarization rotates as it moves through layers of field-stressed vacuum. The magnetar does not need to touch the light to change it. The field alone is enough. This is not a metaphor. This is quantum mechanics made visible at cosmic scale, an effect predicted by equations written decades before the first magnetar was ever observed. The field is so intense that even empty space behaves differently near it. Light itself bends before reaching the surface. This is the regime where quantum electrodynamics, the theory that describes how light and matter interact, begins to show its edge cases, the predictions that can only be tested in the most extreme environments the universe provides. A magnetar is one of those environments. There are no others accessible to us. We cannot build them. We can only watch them from across the galaxy and read what the light tells us. The strongest force you have ever felt in your life, the pull of Earth's gravity holding you against the ground, is a whisper compared to the magnetic pressure at the surface of a magnetar. If you could somehow stand on that surface, the field would not pull you toward the poles. It would rip the atoms of your body apart long before you arrived. Iron in your blood would cease to behave as iron. The electrons that carry signals through your nerves would spiral into trajectories governed entirely by the field, no longer responsive to the electric potentials of your cells. You would not survive long enough to feel pain. You would simply cease to be structured matter. But you are not there. You are here, 50,000 light-years away. And the field that dominates the magnetar's surface has no grip on you. Distance is the only shield that matters. The field falls off with the cube of distance, and by the time it reaches Earth, it is undetectable, a ghost of a force diluted across the light years. What reaches us instead is light, the afterglow of the field's violence, the X-rays and gamma rays released when the field moves, and the star's crust cracks beneath it. The field is not static, it evolves, it twists. Inside the magnetar, currents of charged particles flow through the superconducting interior, and these currents generate the field, sustain it, amplify it. The magnetar inherited this field from the moment of its birth, when the collapsing core of a massive star spun fast enough to ignite a dynamo, amplifying whatever seed field existed in the progenitor star to a quadrillion times its original strength in the first few seconds of the neutron star's life. But once the field is established, it does not remain passive. It exerts pressure on the crust, the solid outer shell of crystalline matter that encases the star. The crust is harder than diamond, its atomic nuclei locked into a lattice, held together by pressures that would crush any material we have ever synthesized. Yet even this crust is not strong enough to contain the field indefinitely. The magnetic pressure builds over years, over decades, stressing the lattice, bending it, until somewhere deep inside the star a bond breaks. The field does not care about the crust. The crust is an obstacle, a shell that must flex or fracture to accommodate the field's geometry. And when the crust can no longer flex, it fractures. The crack propagates at the speed of sound through neutron-degenerate matter, far faster than sound travels through air or water or rock. The fracture is perhaps 5 kilometers long, a hairline split in a sphere 20 kilometers wide. By human standards, it is a canyon. By the standards of the star, it is a scratch. But the field feels the scratch. The geometry shifts. Magnetic field lines that were anchored in the crust suddenly snap free, reconnecting in new configurations, releasing the energy that had been stored in the twist. That energy does not stay inside the star. It floods outward, as light, as X-rays, as gamma rays, as a pulse of radiation so intense that it crosses 50,000 light-years of space and still arrives bright enough to change the chemistry of Earth's upper atmosphere. This is what happened in December 2004. The field moved, the crust cracked, and we, on the far side of the galaxy, saw the light arrive 200 milliseconds later, carrying the energy of 250,000 years of sunlight. The field is what makes a magnetar different. The field is what makes it extreme. Without the field, a magnetar would be indistinguishable from any other neutron star, a dense remnant spinning in the dark, cooling slowly over billions of years, invisible except to the most sensitive instruments. But the field transforms it. The field makes it loud. The field makes it brief. The field ensures that for 10,000 years, this object will be among the most luminous, most energetic, most extreme phenomena the universe produces. And then the field will fade, and the magnetar will fall silent, and it will join the 30 million others that drift unseen through the galaxy, their fury spent, their light gone out. The field is everything. The field is the story, and the field, in the end, is temporary. It decays. The currents that sustain it lose coherence. The star cools. The magnetic pressure eases. The crust stops cracking. The flares stop. The magnetar becomes a neutron star again, ordinary and cold, no longer capable of bending light or polarizing the vacuum or sending gamma-ray pulses across the width of the galaxy. It remains dense, it remains small, but it is no longer extreme. This is the third rung, the field that breaks physics, the field that lasts 10,000 years and then disappears, the field that makes a magnetar what it is, and the field that ensures it cannot remain that way forever. Not every dying star becomes a magnetar. The conditions have to be exactly right. You have seen what a neutron star is, the collapsed core of a massive star, city-sized, dense beyond comprehension, spinning and sometimes pulsing. You have seen the magnetic field that makes a magnetar different, a quadrillion times stronger than Earth's, intense enough to bend light and warp the vacuum itself. Now we arrive at the moment of creation, the accident of collapse, the narrow doorway through which only a few stars pass. A magnetar forms during the core collapse of a massive star in a supernova explosion, the same process that creates every neutron star. The same catastrophic implosion, the same rebound shockwave, the same ejection of the star's outer layers into space. But somewhere in those first seconds, something else happens. The conditions align, the rotation is fast enough, the dynamo ignites. According to the dominant scientific explanation, a magnetar is born when the collapsing stellar core rotates with extraordinary speed, spinning with an initial period shorter than approximately 3 milliseconds, faster than the eye can follow, faster than most pulsars ever achieve. In those first seconds after the collapse, if the core is spinning fast enough, a dynamo ignites inside the newborn star. Convection currents churn through the proto-neutron star's interior. Differential rotation, layers spinning at different speeds, twists and stretches the magnetic field lines. The field amplifies. It grows. Within seconds, it reaches a strength that no other process in nature can match. The mechanism is called an alpha-omega dynamo. The name is borrowed from the same process that generates the sun's magnetic field, but here, compressed into a sphere 20 kilometers wide, spinning hundreds of times per second, the dynamo operates at an intensity that has no parallel. The magnetic field climbs from the trillion Gauss range of an ordinary neutron star to 10 quadrillion Gauss in the span of a few heartbeats. It locks into the crust. It threads through the core. It becomes the defining feature of the star's existence. This is not the only way a magnetar might form. Some scientists propose that the field is inherited, a fossil field, amplified from the magnetic flux of the progenitor star itself, concentrated during collapse. Others suggest that the dynamo operates later, during the cooling phase. The debate continues. But the alpha-omega dynamo model, proposed in the early 1990s, remains the framework most widely used to explain what astronomers observe. The word magnetar is barely 30 years old. The objects themselves are billions of years in the making. Robert Duncan and Christopher Thompson coined the term in their 1992 paper, the foundational work that connected the extreme magnetic fields to the bursts of X-rays and gamma rays that satellites had been detecting for years. Before that paper, the objects were known only as soft gamma repeaters, named for their behavior rather than their nature. Duncan and Thompson gave them a name that captured what they are. Stars defined by magnetism. Stars whose fields are so strong they power everything the star does. But the star that becomes a magnetar does not know it will become one. It lives for millions of years as an ordinary massive star, fusing hydrogen, then helium, then carbon and oxygen and silicon, climbing the nuclear ladder until its core is iron and the fusion stops. The collapse happens in less than a second. The core implodes. The protons and electrons merge into neutrons. The rebound sends a shock wave outward through the star's envelope, tearing it apart, scattering it across light years. What remains is the core, a neutron star, spinning, cooling, settling into its new geometry. If the rotation is fast enough, the dynamo ignites. If the rotation is too slow, the star becomes an ordinary pulsar, still magnetic, still spinning, but not extreme. The difference is a matter of milliseconds. A difference in the angular momentum of the collapsing core, determined by the rotation of the progenitor star, by the way it lost mass during its life, by the turbulence in the supernova explosion itself. Accident and inevitability woven together. The progenitor stars that become magnetars are thought to be massive, perhaps 20 to 40 times the mass of the Sun. They are short-lived by stellar standards, burning through their fuel in a few million years before collapsing. They may be rapidly rotating before they die, spinning faster as they shed their outer envelopes, or they may gain their spin during the collapse itself, through asymmetries in the explosion. The details are still being worked out. What is clear is that magnetars are rare. Only a small fraction of massive stars become neutron stars, and only a small fraction of neutron stars become magnetars. Astronomers estimate that there are perhaps a few dozen active magnetars in the Milky Way at any given time. A few dozen stars, scattered across a galaxy of 400 billion, radiating at the edge of what physics allows. And for every active magnetar visible today, there may be millions that have already faded, their fields decayed, their fury spent. But in the moment of birth, the magnetar does not know its life will be brief. It only knows the spin, the collapse, the ignition of the field. The dynamo operates for seconds. The field it creates lasts for thousands of years. The star that made the field lived for millions. It is a cascade of timescales, each one shorter than the last, converging on a single object 20 kilometers wide, spinning in the dark, wrapped in a magnetic field strong enough to strip the electrons from atoms at a distance of 1,000 kilometers. This is how a magnetar is born. Not through intention, not through design, but through the alignment of rotation and collapse, through the accident of spin. At the moment the core implodes. The universe does not ask permission. The star collapses, the dynamo ignites, the field rises, and in the first seconds of its existence, the magnetar becomes the most magnetic object the universe has ever made. The crust begins to solidify almost immediately. The outer layers of the neutron star cool and crystallize into a lattice, harder than diamond, harder than any material that exists on Earth. The field threads through it, locking into the crystalline structure, exerting stress from the moment the star is born. The magnetar does not rest. The field is already moving beneath the surface, already twisting through the interior, already building pressure against the crust that confines it. The first starquake may be years away, or decades, but the conditions for it are set in these first moments. For now, in the first seconds, the magnetar is simply new, a newborn star with a field that will define everything it does for the next 10,000 years. It spins in the remnant of the supernova, surrounded by the debris of the star it once was, glowing not from fusion, but from the heat of its own collapse, and the energy stored in its magnetic field. It is alone, it is extreme, it is the result of millions of years of stellar evolution compressed into a single moment of alignment, the accident of collapse, the precision of rotation, the ignition of the dynamo. This is the doorway. Only a few stars pass through it. The rest become ordinary neutron stars, or black holes, or disperse entirely. But the ones that pass through this doorway become something else. They become the loudest, briefest, most extreme objects the universe knows how to make. And once the field is set, once the dynamo has done its work, the magnetar begins its short, fierce life. The crust of a magnetar is solid. Harder than diamond, harder than any material that exists on Earth. A crystalline lattice of atomic nuclei packed so tightly that the space between them vanishes. This crust forms a shell roughly 1 kilometer thick, wrapped around a star the size of a city. Beneath it, the magnetic field moves. It twists, it builds, it exerts pressure against the crust from below. The field is never still. Over years, over decades, the stress accumulates. The crust holds. It holds until it cannot. Then it cracks. When the crust of a magnetar fractures, the event is called a starquake. The name sounds almost gentle, almost familiar, but the scale is nothing like the tremors that move through the surface of a planet. A starquake is the sudden failure of a material under forces that would vaporize any substance we know. The crust splits. Fractures race across the surface, 5 kilometers long, 10 kilometers, carving through the lattice in milliseconds. The star's shape shifts. The magnetic field, twisted and compressed for decades, suddenly rearranges itself. The energy stored over all those years releases at once. What happens next is a flare. The fracture triggers a cascade. Magnetic field lines snap and reconnect, or the crust itself shifts and drags the field with it. The exact mechanism remains uncertain. Some models favor crustal cracking as the primary driver. Others point to sudden reconnections in the twisted magnetosphere above the star, where field lines tangle and release like coiled springs. Both mechanisms may be at work. The debate continues, not because the observations are unclear, but because the physics at these extremes operates in regimes we cannot replicate. Either way, the result is the same. Energy that accumulated slowly, patiently over decades, erupts in a fraction of a second, as a burst of X-rays and gamma rays so intense that it floods the space around the star. The 2004 event from SGR 1806-20 was the first time humans observed direct evidence of a neutron star's crust cracking. Satellites designed to study Earth's magnetosphere, the European Space Agency's cluster and double star missions, happened to be watching when the flare arrived. They were not looking for magnetars. They were measuring the solar wind, the flow of particles from our own sun. But on the morning of December 27th, they recorded something else. The gamma rays from the flare carried with them a signature, a pattern in the energy distribution, that could only have come from fractures in the crust itself. The observations matched the predictions. The crust had split. The star had broken its own surface. The fractures inferred from those observations were approximately 5 kilometers long. 5 kilometers of crystalline material, denser than anything in our experience, sheared apart in an instant. Imagine a crack running the length of a city, not through soil or rock, but through a substance held together by gravity so intense that it bends space-time around it. The crack does not propagate slowly. It does not give warning. It moves at a significant fraction of the speed of sound in neutron-degenerate matter, which is to say thousands of kilometers per second. The crust does not crumble. It fractures cleanly, precisely, and the magnetic field trapped beneath it surges outward. Most starquakes are smaller. Most release bursts that last a few tenths of a second, bright enough to be detected across the galaxy but brief, contained. These are the routine flares, the minor fractures, the adjustments a magnetar makes as its field slowly decays. They happen every few weeks, every few months, unpredictable but frequent. The star cracks, the field releases, the flare fades. Then silence returns. But every few decades, perhaps once in a century, a magnetar produces a giant flare. The fracture runs deeper. The rearrangement is more violent. The energy release is not a burst but a flood. The 2004 event was one of these. Only twice before had astronomers recorded anything comparable. In 1979, a magnetar designated SGRO 52666 released a giant flare. In 1998, another, SGR 1900+14, did the same. Both events were extraordinary. Both were studied, catalogued, analyzed. The 2004 flare from SGR 1806-20 was 100 times more energetic than either of them. The flare begins with the initial spike the moment the crust cracks and the field reconnects. This is the brightest phase, the phase that saturated every gamma-ray detector in orbit, the phase that ionized Earth's atmosphere from a distance of 50,000 light-years. It lasts a fraction of a second. Then the flare enters its second phase. The energy does not stop. It continues, oscillating, pulsing, as the star's surface vibrates in the aftermath of the quake. The magnetosphere rings like a bell. The oscillations are regular, periodic, each pulse slightly weaker than the last. This tail phase can last for minutes, sometimes hours, a fading echo of the initial rupture. During this time, the star is radiating across the electromagnetic spectrum, X-rays, gamma rays, radio waves. The surface glows, the field twists and realigns, the crust settles into a new configuration, slightly different from before, the fractures now frozen into the lattice. The star has changed shape, its magnetic field has shifted, the starquake has rewritten the geometry of the object. And then, slowly, the light fades, the oscillations dampen, the magnetosphere quiets, the flare ends. The magnetar returns to its baseline state, still spinning, still radiating, but no longer in outburst. The crust begins accumulating stress again. The cycle resumes. You might imagine that a starquake would destroy the star, that a fracture running kilometers deep through a crust held together by forces we can barely comprehend would shatter the object entirely. But the crust does not shatter, it cracks, it shifts, it releases energy, but it holds. The material is too dense, the gravity too strong. The star remains intact. The fractures heal, not in the sense that the crust repairs itself, but in the sense that the new configuration is stable. The crust has found a new equilibrium. The star continues. This is what a magnetar does. It builds tension, it cracks, it flares, it settles, it waits. The cycle repeats, over and over, throughout the magnetar's active life. Each starquake is unique. Each flare carries a different signature. But the pattern is the same. The field moves. The crust cannot keep up. The star breaks itself again and again until the field is no longer strong enough to fracture the crust, until the magnetar fades into silence. The flares are not random. They follow a pattern, a rhythm set by the decay of the magnetic field. In the first 1,000 years of a magnetar's life, the flares are frequent, intense. The field is at its strongest. The crust cracks often. As the millennia pass, the field weakens. The flares become less frequent, less energetic. The starquakes grow smaller. By the time the magnetar reaches the end of its active phase, 10,000 years after its birth, the flares have stopped entirely. The field is still present, still stronger than that of an ordinary neutron star, but no longer strong enough to crack the crust. The magnetar goes quiet. What remains is a cooling, spinning neutron star, indistinguishable from the millions of others scattered across the galaxy. Its crust is scarred, fractured, a record of the violence it once endured. But the violence has ended. The field has decayed. The star is silent now, and it will remain silent for the rest of time. The 2004 flare was a glimpse of this process, a single moment in the life of a star that had been cracking its own surface for thousands of years. The flare reached Earth as a wave of gamma rays, traveling at the speed of light across 50,000 light-years of empty space. It arrived on a December morning, unannounced, brighter than anything astronomers had ever recorded from beyond the solar system. It lasted 200 milliseconds. And then it was over. But the star is still there, still spinning, still cracking. Somewhere on the far side of the galaxy, hidden behind the galactic center in the constellation Sagittarius, SGR 1806-20, continues its slow decay. The magnetic field still twists beneath the crust. The stress still builds. Another starquake will come, perhaps in a year, perhaps in a decade. When it does, the flare will race outward at the speed of light, crossing the galaxy in silence, arriving here 50,000 years later as a brief pulse of gamma rays, a whisper from a star the size of a city that broke its own surface and sent the evidence across half the Milky Way. The 2004 flare was not the last. It was simply the one we saw. On the 27th of December, 2004, the brightest gamma-ray flare ever recorded outside the solar system reached Earth from a magnetar called SGR 1806-20, 50,000 light-years away, on the far side of the galaxy. In 200 milliseconds, it released as much energy as our Sun radiates in 250,000 years. Every gamma-ray instrument in orbit saturated at once. The ionosphere changed from night to day. Astronomers around the world looked up at the data and realized they had just witnessed something that had happened only twice before in recorded history. In 1979, a magnetar designated SGR 52666 had sent a flare toward Earth. In 1998, another called SGR 1900+14 had done the same. Both events had been extraordinary. Both had marked the first direct evidence that objects like this existed at all. The 1979 flare had arrived without warning, a burst of gamma rays so intense that satellites designed to detect nuclear weapons tests recorded it as something entirely new. The 1998 event confirmed the pattern. Astronomers began to understand that these were not singular accidents but a category of object, a class of neutron star, whose magnetic field was strong enough to tear itself apart. But the flare from SGR 1806-20 was 100 times more energetic than either of those. It was not simply brighter. It was an entirely different order of magnitude, a signal so powerful that it arrived across 50,000 light-years and still changed the chemistry of the sky above you. The satellites that detected it were not designed to study distant stars. Many were watching the Sun, others were mapping Earth's magnetosphere, tracking the invisible currents that flow between our planet and the solar wind. But on that December morning, every instrument capable of detecting gamma rays recorded the same thing at the same instant. The detectors did not measure the flare. They were overwhelmed by it. The signal was too bright to fit within the range of their sensors, and so the data they returned was not a curve but a flat line, a ceiling struck and held for the duration of the pulse. Engineers reviewing the telemetry assumed at first that the instruments had malfunctioned. It took hours to confirm that every satellite in orbit had seen the same thing, that the saturation was not a failure but a consequence of the brightness itself. The flare's reflection off the surface of the Moon was bright enough to be measured. Astronomers used it to confirm the direction and intensity of the burst. The light had traveled 50,000 years through the dark, crossing the width of the galaxy, passing through clouds of gas and dust and the gravitational wells of 100 billion stars. And when it reached the Moon, it was still strong enough to bounce. The reflection was faint by human standards, but detectable by instruments sensitive enough to track gamma rays ricocheting off lunar regolith. It became another data point in the reconstruction of what had happened. At 50,000 light-years, the flare reached us as a whisper that ionized the upper atmosphere and saturated every detector we had pointed toward the sky. Astronomers have calculated that if SGR 1806-20 had been located within 10 light-years of Earth, the same flare would have stripped away the ozone layer and triggered a mass extinction. The distance saved us. The distance always saves us. 10 light-years is the distance to a handful of nearby stars, close enough that we have sent probes in their direction. 50,000 light-years is the distance across half the galaxy, far enough that the light we see tonight left its source before humans learned to write. SGR 1806-20 is not simply a magnetar, it is the most magnetic object ever observed. Its field reaches strengths near 10 to the 15th Gauss, a quadrillion times stronger than the magnetic field that surrounds the Earth. That field is not static. It moves. It twists. It stores energy the way a bent steel beam stores tension. And when the structure can no longer hold, it releases everything at once. The field is so intense that even empty space behaves differently near the star. Light itself bends before reaching the surface, polarized and twisted by quantum effects that exist only in the presence of fields this strong. No laboratory on Earth can replicate what exists on the surface of a magnetar. We can produce magnetic fields of 10 million Gauss for fractions of a second in controlled explosions. A magnetar sustains fields 100 million times stronger for thousands of years. The two earlier giant flares, in 79 and 98, had been the first confirmation that magnetars were real. Before those events, the existence of neutron stars with magnetic fields this strong was a theoretical prediction, a consequence of equations describing what might happen during the collapse of a massive stellar core. The flares turned theory into observation. They gave astronomers a way to measure the field strength directly, to watch the consequences of a starquake in real time. The word magnetar itself is barely 30 years old. The objects it describes are billions of years in the making. The 2004 event was different because of its scale. It was not the first giant flare, it was the most powerful. It came from a magnetar whose field was already known to be among the strongest ever measured, and it arrived with an intensity that allowed scientists to study not just the fact of the flare, but its structure. The initial spike lasted 200 milliseconds. After that, the flare decayed into a pulsing tail that continued for several minutes, modulated by the rotation of the star itself. The star was spinning once every 7.5 seconds, and each rotation left a signature in the fading light, a rhythm that told astronomers the shape of the object that had cracked. The pulsations were not random. They were a clock, a record of the star's rotation encoded in the decay of the light, and from that clock, scientists could infer the geometry of the fracture, the way the magnetic field had rearranged itself, the direction in which the energy had been released. The European Space Agency's cluster mission and the Chinese double-star satellites, both designed to study Earth's magnetic environment, happened to be in position to observe the flare's effect on our planet's magnetosphere. They recorded the first direct observational evidence of fractures in a neutron star's crust. The data suggested cracks approximately 5 kilometers long, running through a surface where a sugar cube of matter weighs as much as all of humanity. The crust had broken. The field had rearranged itself. The energy stored over years or decades had been released in a fraction of a second, and the light from that release had traveled across half the galaxy to reach us. The satellites had been watching Earth. They ended up watching a star crack open 50,000 light-years away. This was not the first starquake ever detected. But it was the brightest, the best observed, and the one that allowed scientists to connect the theory of magnetic field decay and crustal stress to a specific, measurable event. SGR 1806-20 sits in the constellation Sagittarius, hidden behind the galactic center, embedded in a region so dense with stars and gas that optical telescopes cannot see it. The only reason we know it exists is because of the radiation it emits. Gamma rays do not care about dust. They pass through the galaxy as if it were empty, carrying information from objects we will never photograph, never resolve as points of light, but whose physics we can read in the shape of the signal they send. The flare traveled through a galaxy thick with matter, through molecular clouds and stellar nurseries, and the diffuse glow of 100 billion suns, and it arrived at Earth, still carrying the signature of the event that created it. The flare reached us 50,000 years after it left the surface of the star. 50,000 years ago, humans on Earth were beginning to paint images on cave walls, to tell stories. to map the night sky with names and myths. The light that arrived in 2004 had been traveling since before any of that. It had crossed a distance so vast that the galaxy itself had rotated a fraction of a degree in the time it took to arrive. And when it reached us, it was still powerful enough to change the ionosphere, to saturate our instruments, to remind us that the universe contains objects whose behavior we can measure but not replicate. The 2004 event was not a threat, it was a message. It told us that magnetars exist, that their fields are as strong as the equations predict, that their crusts can fracture, that the energy released in those fractures can cross the width of the galaxy and still be detected. It told us that the universe operates at scales we do not experience, that the boundaries of physics are written not in textbooks, but in the behavior of objects like this. Objects that live for 10,000 years and spend that entire brief life at the edge of what matter and spacetime can sustain. You are drifting now, 50,000 light-years from the surface of a star the size of a city, a star whose magnetic field is so intense that empty space itself behaves differently in its presence, a star that cracked its own crust and sent the evidence across the galaxy to reach you on a December morning in 2004. The light has already arrived, the ionosphere has already returned to its usual state, the satellites have already recorded the data. The star is still there, still spinning, still storing energy in its twisted field, but the next moment it cracks, the light will take 50,000 years to reach you. A magnetar burns at its most extreme for about 10,000 years. Then the field begins to fade, the starquakes grow quieter, and the brightest object in the galaxy becomes just another neutron star, cold and silent, indistinguishable from the dark. 10,000 years. The sun has been burning for 4.5 billion years. By cosmic standards, a magnetar's active life is the blink of an eye. Consider the proportion. Millions of years to build the progenitor star, layer by layer, fusing hydrogen into helium, helium into carbon, carbon into oxygen, silicon, iron. Millions of years of evolution, of mass accumulation, of the slow march toward collapse. Then the core gives way in seconds, the dynamo ignites, and for 10,000 years the object screams across every wavelength we can measure. And then it goes quiet. The field decays. The crust stills. The star that once ionized a planet's atmosphere from 50,000 light-years away becomes a relic, spinning in silence, invisible to every instrument we have pointed at the sky. Millions of years of evolution to create it, 10,000 years of fire, then silence. We have seen, perhaps, 30 magnetars in our galaxy, all of them still active, still flaring, still young enough to announce themselves. But the galaxy may contain 30 million magnetars we can no longer see. 30 million extinct volcanoes of the cosmos, still and cold, their brief fury long spent. They are out there now, scattered across the spiral arms, orbiting the galactic center in the same slow procession as every other star. But they have nothing left to say. Their magnetic fields have decayed below the threshold that powers starquakes. Their crusts no longer crack. They emit no gamma rays, no X-rays, no radio pulses. They are neutron stars like any other, dense and spinning and unremarkable, and unless one passes directly between us and a more distant light source, we will never know it was once a magnetar. 30 million silent giants. 30 million objects that once released more energy in 1/10 of a second than our sun will produce in 250,000 years, now invisible, their stories told only in the faint chemical signatures they left behind in the gas clouds they once illuminated. The proportion is difficult to hold in your mind. A human lifetime is perhaps 80 years. 10,000 years ago we were just beginning to plant seeds. Civilization as we understand it, cities, writing, the first empires, is younger than the active life of a single magnetar. And yet in the life of the galaxy, 10,000 years is nothing. The Milky Way is 13 billion years old. A magnetar's active phase is less than 1/1,000,000th of that span. If the galaxy's lifetime were compressed into a single year, a magnetar would flare for 3 seconds. 3 seconds of fire. Then the rest of the year in silence. And because their lives are so brief, and because the conditions that create them are so rare, we are living in a galaxy that is mostly populated by their ghosts. For every magnetar we can see, there may be 1,000,000 we cannot. The stars that became magnetars millions of years ago, when the galaxy was younger and the rate of supernovae higher, have long since faded. Their fields are gone. Their heat radiated away. They are 20-kilometer spheres of neutron degenerate matter, spinning once every few seconds, cooling slowly toward the background temperature of space. And they will remain that way for billions of years, perhaps forever, unless something disturbs them. This is the cost of extremity. The magnetic field that allows a magnetar to crack its own crust, to release more energy in a fraction of a second than most stars produce in millennia, is also the thing that consumes it. The field does not last. It decays. The energy that powers the starquakes is drawn from the rotation of the star itself, and from the slow unwinding of the magnetic field lines twisted through the crust and core. As the field weakens, the stress on the crust diminishes. The starquakes grow less frequent, less violent. The flares dim. And eventually, the magnetar crosses a threshold below which it can no longer sustain the feedback loop that made it visible. It becomes inert, not dead. A neutron star cannot die in any conventional sense, but dormant, spent, an ember that has cooled below the point of light. The irony is that we are only able to study magnetars because they are young. The objects we have catalogued, the 30 or so confirmed magnetars in the Milky Way, are all still in their active phase. They are still flaring. They are still cracking. SGR 1806-20, the magnetar that sent the 2004 flare across 50,000 light-years of space, is young by magnetar standards. It may have been born 10,000 years ago, or 5,000, or 15,000. We do not know precisely, but it is still burning. It is still capable of the kind of starquake that changes a planet's ionosphere from the far side of the galaxy. In another 10,000 years, it may not be. The field will have decayed. The crust will have settled into a new equilibrium. The star will still be there, still spinning, still dense beyond comprehension. But it will no longer be a magnetar in any functional sense. It will be a neutron star, one among hundreds of millions. And unless we happen to be looking at exactly the right patch of sky with exactly the right instrument, we will never know it was once extraordinary. This is the tragedy and the gift of brevity. Because magnetars live such short lives, they are always rare. At any given moment, only a handful are active in the galaxy. But because the galaxy is old, and because stars have been dying and collapsing for billions of years, the total number of objects that were once magnetars is staggering. 30 million silent remnants. 30 million stars that once bent light with magnetic fields alone, that once cracked their own crusts, that once released the energy of 250,000 years of sunlight in the time it takes to blink. And all of them are still here. They have not vanished. They have not evaporated. They are simply waiting, spinning in the dark, cooling slowly, their stories written in the faint glow of residual heat and the subtle gravitational perturbations they exert on anything passing nearby. You could be looking at one right now and not know it. A faint point of light in a crowded star field, no different from the thousands of other neutron stars scattered across the plane of the galaxy. But once, millions of years ago, it was the loudest object in the sky. Once, it sent a flare across the spiral arms that lit up gas clouds hundreds of light-years away. Once, it was a magnetar. Now it is a memory, spinning in silence, And the only record of what it was is the faint chemical signature it left in the nebulae it once illuminated, and the fact that it is still here, still dense, still strange, still a neutron star. The universe does not preserve its extremes. It creates them, briefly, and then lets them fade. The loudest objects it has ever made burn for 10,000 years, and then spend the rest of eternity in silence. And because we are here now, in this brief window of cosmic time, we are able to see a few of them before they go quiet. We are able to watch SGR 1806-20 crack its crust and send a flare across 50,000 light-years. We are able to record the gamma rays, measure the field strength, infer the fracture, and understand, for the first time, what a star does when it is strong enough to break itself. But we are also living in a galaxy filled with the ones we missed, the ones that flared before we were here to see it, the ones that went silent a million years ago, or 10 million, or 100 million. They are still out there, scattered across the disk, spinning in the dark, and they will remain there long after the last active magnetar has faded, long after the last starquake has echoed across the galaxy, long after the conditions that create magnetars have ceased to exist. 30 million silent giants. The briefest lives in the cosmos, and the longest silence. The magnetic field of a magnetar exists at the edge of what physics can describe. Beyond a certain point, the equations we use to understand matter and energy begin to falter. They approach their limits, and what lies beyond those limits remains one of the open frontiers of science. A magnetar is not simply an object we study from a distance. It is a laboratory we could never build, conducting experiments we could never design, revealing truths about the universe that no human instrument can replicate. The strongest magnetic field ever produced on Earth reached approximately 10 million Gauss. It existed for a fraction of a second, inside an explosion, under conditions that destroyed the equipment that created it. A magnetar's field is 100 million times stronger than that. No laboratory on Earth can recreate what exists on the surface of a magnetar. We can only watch from 50,000 light-years away and read what the physics tells us. Inside that field, matter behaves in ways that defy ordinary experience. The vacuum itself becomes something different. Empty space in the presence of a magnetar's magnetic field is no longer truly empty. Light passing through the region near the surface is polarized and bent not by gravity, not by matter, but by the field alone. This is a quantum electrodynamic effect called vacuum birefringence. It is predicted by the equations of quantum field theory, and it has been observed in laboratories under carefully controlled conditions. But near a magnetar it happens continuously, at scales and intensities that turn theory into spectacle. The field is so intense that even the vacuum responds to it, as though space itself has texture. At these densities, at these field strengths, the matter inside a neutron star enters states that have no counterpart anywhere else in the universe. The core is not simply compressed, it is transformed. Neutrons packed so tightly together that they may dissolve into their constituent quarks, particles that exist only in theory, or in states for which we have no name yet. Some physicists believe the core may contain matter that obeys equations we have not yet written. The boundary between what we know and what we do not know runs directly through the center of every magnetar. We know that neutrons are made of quarks. We know that under ordinary conditions, quarks are confined within protons and neutrons. But inside a neutron star, the pressure is so extreme that confinement may break down. The quarks may exist freely, forming a quark-gluon plasma, or something stranger still. The equations of quantum chromodynamics, the theory that describes the strong nuclear force, become extraordinarily difficult to solve at these densities. We can simulate them on supercomputers, but the results depend on assumptions we cannot verify. The only place in the universe where those assumptions are tested is inside a neutron star, and we cannot see inside. A magnetar adds another layer of complexity. The magnetic field inside the star is not uniform. It twists and coils, exerting pressure on the matter around it. In some regions, the magnetic field may be strong enough to alter the structure of matter itself, creating states that exist nowhere else. The field may suppress certain particle interactions or enhance others. It may change the way heat flows through the core or the way the crust responds to stress. Every starquake, every flare, every gamma-ray burst is a message from the interior, written in a language we are still learning to read. The physics of magnetars forces us to confront the limits of our understanding in multiple domains simultaneously. General relativity describes how spacetime curves around massive objects, and a neutron star curves spacetime more sharply than almost anything except a black hole. Quantum mechanics describes how particles behave at the smallest scales, and inside a neutron star, quantum effects dominate the behavior of matter at densities that dwarf anything we can produce. Quantum electrodynamics describes how light and matter interact in the presence of electromagnetic fields, and a magnetar's field pushes those interactions into regimes where the standard approximations no longer hold. No single theory covers all of these domains at once. We have general relativity for gravity, quantum field theory for particles and forces, and nuclear physics for the behavior of atomic nuclei. But at the center of a magnetar, all three regimes overlap. The equations do not fit together cleanly. There are gaps, approximations, unsolved problems. The magnetar does not care. It exists anyway, indifferent to the limits of our mathematics. When we observe a magnetar, we are not simply observing an object. We are observing a test of our theories. Every flare, every oscillation, every shift in the magnetic field is a data point that tells us whether our equations are correct or whether we need new ones. The 2004 event was not just a burst of energy. It was a message from the edge of physics, carried across 50,000 light-years, arriving in our instruments as a cascade of gamma rays that no one had predicted and no one fully understands, even now. There are questions we can answer about magnetars. We can measure their rotation periods, their magnetic field strengths, their distances, their ages. We can count the flares they produce and calculate the energy they release. But there are deeper questions that remain open. What is the exact state of matter in the core? How does the magnetic field evolve over time? Why do some neutron stars become magnetars, while others do not? What happens to the star after the field is gone? These are not questions we can answer by building a magnetar in a laboratory. We can only answer them by watching, by waiting, by listening to the signals that reach us from across the galaxy. Every magnetar we observe is unique. Every flare is unrepeatable. The universe does not perform controlled experiments. It simply unfolds, and we do our best to understand what we see. The fact that magnetars exist at all is a reminder that the universe is more extreme than our theories anticipated. When the first magnetar was identified in the early 1990s, it was a surprise. The models of neutron star formation did not predict magnetic fields that strong. The observations forced the models to change. And as we observe more magnetars, as we gather more data, the models continue to evolve. The edge of physics is not a fixed line. It moves as we learn. A magnetar is a place where the universe reveals itself at its most uncompromising. No atmosphere to soften the view, no distance to blur the details. Just matter and energy and spacetime, pushed to their breaking points, obeying laws we are still discovering. It is a laboratory without walls, an experiment without a hypothesis, a signal without a sender. It is the cosmos doing what it does, indifferent to whether we are watching. And yet we do watch. We build satellites to detect the gamma rays. We write equations to describe the fields. We construct theories to explain the flares. We listen to the signals that arrive from 50,000 light-years away, and we try to read the story they tell. The magnetar does not know we are listening. It simply exists, at the edge of what is possible, waiting for us to catch up. You have traveled with us through the birth of a magnetar, through the collapse that ignited its field, through the crust that cracked under forces no human laboratory will ever recreate. You have heard the story of a flare that crossed 50,000 light-years and arrived on a December morning in 200 milliseconds, carrying 250,000 years of sunlight, compressed into a flash that changed the chemistry of our sky. You have learned that this fury lasts only 10,000 years before it fades. 10,000 years. By the measure of stars, this is nothing. The sun has been burning for 4.5 billion years, and will burn for 4.5 billion more. But a magnetar burns at its brightest for 10,000 years, and then it goes quiet. The field that twisted spacetime and bent light and cracked the crust from within begins to decay. The starquakes grow less frequent. The flares dim. The gamma-ray observatories that once tracked its outbursts lose the signal. And within a few tens of thousands of years, the magnetar becomes indistinguishable from any other neutron star, spinning in the dark, its magnetic field reduced to a whisper, its fury spent. The progenitor star lived for millions of years before its death. Millions of years of fusion, of hydrogen becoming helium, becoming carbon, becoming iron, the slow, patient work of stellar alchemy. And then, in a fraction of a second, the core collapsed. In the first seconds after that collapse, if the conditions were exactly right, a dynamo ignited inside the newborn neutron star and amplified the magnetic field to 1,000,000,000 times the strength of Earth's. Millions of years of evolution to create it, 10,000 years of fire, then silence. Astronomers estimate there may be 30 million of them in our galaxy alone. 30 million magnetars that once roared, that once released in milliseconds the energy a star takes centuries to gather, that once twisted the vacuum itself into shapes we are only beginning to understand. They are still there, these silent giants. They circle the galactic center, in orbits older than our species, each one a city-sized sphere of matter, compressed beyond the threshold of ordinary physics. Each one carrying within it the memory of a collapse that happened millions of years ago. They are invisible now. Their fields have faded below the threshold that powers the flares. They no longer crack their crusts. They no longer send gamma rays racing across the galaxy to ionize the atmospheres of distant worlds. They spin, as neutron stars do, but they do not call attention to themselves. Their crusts, once fractured by starquakes powerful enough to release the energy of 100 supernovae in 1/10 of a second, are now still. The magnetic field lines that once reconnected and snapped and hurled gamma rays into the void have settled. The tension is gone. The violence has passed. But for 10,000 years they were the loudest objects in the galaxy, louder than supernovae, which flash once and fade. Louder than black holes, which swallow light and leave only the echo of what they consume. A magnetar in its active phase is a star that refuses to go quietly, that takes the energy of its own collapse and releases it not in a single explosion, but in a series of fractures, each one a crack in the hardest substance the universe has ever made. Each one a flare that crosses light years and arrives as a pulse of gamma rays bright enough to saturate every detector pointed in its direction. Each flare is a message written in the only language the universe speaks, the language of energy and time and distance. And then, After 10,000 years, silence. The silence is louder than the flares. 30 million magnetars, scattered through the disk of the galaxy, each one a former giant, each one now indistinguishable from the dark. They outnumber the active magnetars by thousands to one. For every magnetar we can detect, there are thousands we will never see, whose fields have already decayed, whose crusts no longer crack, whose stories have finished. The active magnetars are the exceptions, the youngest members of a population that stretches back billions of years. Most magnetars have already gone quiet. Most of them finished their active lives long before our sun was born. You have been listening to the echo of one of them. SGR 1806-20, 50,000 light-years away, hidden behind the galactic center in the constellation Sagittarius. A star the size of a city with a magnetic field a quadrillion times stronger than Earth's. On the 27th of December, 2004, its crust fractured. The energy stored over years of magnetic tension released in 200 milliseconds. The flare crossed the galaxy, carrying the equivalent of 250,000 years of sunlight. And it arrived here, at this small blue world on the edge of a spiral arm. And it changed the ionosphere for a moment, and then it passed. The universe does not repeat itself. That flare, the brightest ever recorded, will not come again from that star. SGR 1806. The 20th of May, flare again. Smaller bursts as its crust continues to crack, but the giant flare of 2004 was singular. It was the third giant flare ever observed, 100 times more powerful than the two that came before it in 1979 and 1998. And in a few thousand years, perhaps 10,000, perhaps less, SGR 1806-20 will join the 30 million silent magnetars that circle the center of the galaxy tonight. Their fields are gone, their fury spent. They were the loudest things the universe ever made, and now they are indistinguishable from the dark. You have been listening to an echo from 50,000 light-years away, across 250,000 years of sunlight, arriving in 200 milliseconds. You can rest now. On the 27th of December 2004, something arrived at Earth from the other side of the galaxy. It came as gamma rays, traveling 50,000 years across the Milky Way, crossing the galactic center, threading the dust lanes of Sagittarius, arriving in a flood that lasted 0.2 of a second. Every gamma-ray instrument in orbit saturated simultaneously. The signal was so bright that its reflection off the Moon's surface was detectable. The flare ionized Earth's upper atmosphere, changing the ionic density of the ionosphere in a way that was recorded around the globe. A scientist named Victoria Caspi would later say it changed our ionosphere from night to day. The source was SGR 1806-20, a star 50,000 light-years away, hidden behind the galactic center. In the first 200 milliseconds of that flare, it released as much energy as our sun radiates in 250,000 years. The star that did this is the width of a city. A neutron star is what remains after a massive star dies. The core collapses inward until there is nowhere left to go. What you are left with is a sphere roughly 20 kilometers across, containing about 1.5 times the mass of the Sun, the size of a city, the weight of a star. A sugar cube of neutron star material would weigh as much as all of humanity. Every person alive, compressed into something you could hold between your thumb and forefinger. The matter inside is so tightly packed that atoms themselves have collapsed. Electrons and protons merge into neutrons. The entire star becomes a single atomic nucleus, held together by gravity balanced against the resistance of neutrons that refuse to occupy the same quantum state. Neutron stars spin. Many emit beams of radio waves as they rotate, sweeping across space like lighthouse beams. These are pulsars, the clocks of the cosmos. A magnetar is a neutron star born under specific conditions that amplify its magnetic field to strengths that break the ordinary rules. Where a typical neutron star might have a field 1,000,000,000,000 times stronger than Earth's, a magnetar's field reaches 1,000,000,000,000 times stronger. Earth's magnetic field measures about half a Gauss at the surface. A refrigerator magnet is about 100 Gauss. An MRI machine reaches 10,000 Gauss. An ordinary neutron star has a field of 1,000,000,000,000 Gauss. A magnetar reaches 1,000,000,000,000. At that strength, the field bends light. Not through gravity, but through the magnetic field alone. The vacuum itself behaves differently. Empty space becomes something in the presence of that field. Light passing through it is polarized, twisted, refracted, before it ever reaches the star's surface. This is a quantum effect, predicted by equations but almost never seen in nature. Near a magnetar, it is constant. Not every dying star becomes a magnetar. The conditions have to be exactly right. In the first seconds after a massive star's core collapses, if the newborn neutron star is spinning fast enough, a dynamo can ignite. Convection currents combine with differential rotation to amplify the magnetic field in a runaway process. Within seconds, the field climbs from the already extreme trillion Gauss range to the quadrillion Gauss realm of a magnetar. The word itself was coined barely 30 years ago by Robert Duncan and Christopher Thompson. The objects themselves have existed for as long as stars have died. But once a magnetar is born, it does not stay quiet. The crust of a neutron star is solid, a crystalline lattice harder than any material on Earth. The crust is about 1 kilometer thick, and beneath it lies the interior, a sea of neutrons and magnetic field lines, churning, shifting. The magnetic field inside a magnetar is not static, it moves, it twists, and as it does, it exerts stress on the crust above, building tension over years, over decades. The crust resists, it holds, and then, eventually, it does not. When the stress exceeds the breaking point, the crust fractures, the star cracks. In June of 2005, scientists analyzing data from the European Space Agency's cluster and double star missions announced the first direct observational evidence of a crack in a neutron star's crust. The fractures were inferred to be about 5 kilometers long, running through a crust 1 kilometer thick, on a star 20 kilometers wide. When the crust cracks, the magnetic field snaps into a new configuration. The energy stored in the twisted field lines, built up over decades, releases in milliseconds. The result is a flare, a burst of X-rays and gamma rays so intense it can be seen across the galaxy. Most magnetar flares are brief, releasing energies equivalent to what the Sun emits in years. But sometimes the crack is deep enough that the flare becomes something else. It becomes a giant flare. Only 3 times in recorded history have astronomers observed a giant flare from a magnetar. The first was in 1979 from SGR 52666. The second was in 1998 from SGR 1900+14. Both events were extraordinary. The third event was the one that reached Earth on the 27th of December, 2004, from SGR 1806-20. It was 100 times more powerful than either of the previous two. The initial spike lasted 200 milliseconds. In that time, the magnetar released 250,000 years of sunlight. At 50,000 light-years away, the flare was bright enough to change our ionosphere. Astronomers have calculated that if SGR 1806-20 had been located within 10 light-years of Earth, the flare would have obliterated the ozone layer and triggered mass extinction. At 50,000 light-years, it arrived as a whisper that changed the sky. The crust cracked, the field reconnected, the energy stored over decades, released in 1/5 of a second. And then the star settled again, and the long, slow process of building tension began once more. But it will not last forever. A magnetar's active phase lasts about 10,000 years. After that, the magnetic field decays. The crust stops cracking. The flares stop. The magnetar becomes an ordinary neutron star, still dense, still spinning, but no longer extreme. 10,000 years. The Sun has been burning for 4.5 billion years. The massive stars that become magnetars burn for millions of years before collapsing. Millions of years of evolution to create it. 10,000 years of fire. Then silence. Scientists estimate there may be 30 million inactive magnetars in the Milky Way alone. 30 million former magnetars, their fields decayed, their fury spent, now cold and silent. They are extinct volcanoes, their brief eruption over, their heat dissipated into the dark. And yet, in those 10,000 years, they are the loudest things in the universe. Magnetars represent the most extreme natural laboratory we know. The strongest magnetic field ever produced by human hands reaches about 10 million Gauss only for a fraction of a second in controlled explosions. A magnetar's field is 100 million times stronger, and it persists for thousands of years. We cannot build it. We can only watch from 50,000 light-years away and read what the physics tells us. The internal state of matter inside a magnetar remains one of the open frontiers of physics. At these densities, some physicists believe neutrons may dissolve into quarks, or exist in states that have no name yet. The equations approach their limits, and what lies beyond the limit, we do not know. 30 million silent magnetars circle the center of the galaxy tonight. Their fields are gone. Their fury spent. They were the loudest things the universe ever made. And now they are indistinguishable from the dark. You have been listening to an echo of one of them, from 50,000 light-years away, across 250,000 years of sunlight, arriving in 200 milliseconds. The universe does not repeat itself. You can rest now. You have traveled 50,000 light-years tonight to watch a star the size of a city crack its own crust and release 250,000 years of sunlight in less time than it takes to blink. The journey mattered, not because magnetars threaten us, but because they show us what the universe becomes when physics approaches its own limits. Some of you are still awake. Some fell asleep somewhere between the starquake and the silence. Both are exactly right. Wherever you are tonight, in a city, in a room with one window, under a sky you cannot see, the dark will still be here. So will I. Tomorrow night we will map something else together, something equally strange and far away. You are welcome back anytime. Until then, rest. The magnetars have already spent their fire.